tend to picture our solar system as just, hanging out there in the void, quietly minding its own business.
Right, like it's isolated.
Exactly. But what if our little corner of the universe is actually, well, quite special? Maybe even shaped by events of unimaginable power.
Hmm, that's where things get interesting.
So today we're taking a deep dive into the sun's cosmic neighborhood, this region that seems to have been sculpted by stellar explosions millions of years ago.
Yeah, a long, long time ago.
We want to uncover what this region is, how it formed, and what the latest findings are telling us about our actual place on the galactic map.
Consider it your backstage pass to the sun's cosmic address.
Love it. Okay, so kicking things off. The sun isn't just floating in pure emptiness.
No, not at all. It's actually located inside a warm, very thin cloud of interstellar gas.
A cloud, like a gas cloud.
Exactly. It's partially ionized gas, actually. The temperature is pretty warm, around 7,000 Kelvin,
Yeah.
but the density is incredibly low. Think zero point 0.1 particles per cubic centimeter, just incredibly sparse.
Wow, okay, so barely anything there.
Almost nothing. But it's this cloud that the solar wind, that constant stream of particles flowing out from our sun, pushes against.
Ah.
And that creates a kind of protective bubble around our solar system. We call that the heliosphere.
Right, I've heard of the heliosphere. How far out does that go?
It extends a pretty long way, roughly 100 to 150 astronomical units.
And an astronomical unit is the Earth-Sun distance. So 100 to 150 times farther out than Earth is from the sun.
Precisely. Quite a large bubble generated just by our own sun.
Okay, so the sun has its own personal bubble, the heliosphere, inside this thin, warm cloud. But is this, like, everywhere? Is the whole galaxy filled with this stuff?
No, that's the thing. This particular cloud isn't everywhere. It's actually situated within an even larger region of even sparser interstellar gas. That larger region is known as the local cavity.
Local cavity.
And
Hi.
within this local cavity, there's, well, an even more intriguing structure, something called the local bubble.
The local bubble. Okay, now that sounds interesting. Not just a cavity, but a bubble. What exactly is that? Sounds a bit like cosmic bubblegum.
Huh. That's a fun way to put it. But yeah, imagine a huge region, maybe 100 parsecs across.
100 parsecs. That's over 326 light years.
Right. A really big area. And it's filled with incredibly hot, but still very low density gas. We're talking temperatures up around 1,000,000 Kelvin.
1,000,000 Kelvin inside this bubble.
Yeah, hot coronal gas. Initially, scientists kind of inferred its existence because they detected faint, soft X-rays coming from this general area of space.
Soft X-rays, so not something you'd see with a regular optical telescope then.
No, you need specialized instruments.
So what were the first ideas about how this massive hot bubble even got there? What could possibly create something like that?
Well, the early theories pointed towards a couple of possibilities. One was the powerful stellar winds coming from very massive, very hot stars. We call them OB stars.
Yeah.
There's a nearby group of them called the Scosan Association.
OB stars, they live fast and die young, right? Much bigger than our sun.
Exactly. Very energetic lives. The other main idea was that one or maybe several supernova explosions happened nearby, relatively recently in cosmic terms, say, within the last 10 million years or so. That could have blown this bubble.
Supernovae. Okay, that sounds powerful enough. So we have this giant, hot, low-density bubble. How did scientists actually figure out its size, its shape, and, where it came from? It sounds like mapping something invisible.
That's a really good analogy. It was tough. One of the biggest challenges was getting accurate distances to stars in all different directions.
Why distances?
Because the shape of the bubble is basically defined by where we see this hot X-ray emitting gas, and just as importantly, where we don't see absorption from cooler, neutral interstellar gas that should block background light. To know where that boundary is, you need to know how far away the stars are.
Ah, okay. Makes sense.
And before the Hipparcos satellite, our ability to measure distances accurately using ground-based parallax was, well, pretty limited, really only reliable out to about 20 parsecs.
20 parsecs. But the bubble is like 100 parsecs across. That's just a tiny fraction.
Precisely. It wasn't nearly enough. That's why the Hipparcos mission, launched back in '89, was such a game changer.
Right, Hipparcos. I remember that mission.
It gave us much, much better distances for stars, accurately out to maybe 200, 300 parsecs. Suddenly, we could define the local bubble's absorption characteristics much more clearly.
So you could finally see the edges properly.
In a manner of speaking, yes. You could see where the absorbing material stopped. For instance, there was work by Sphere and colleagues in '99. They mapped over 1,000 different lines of sight to various stars.
1,000, wow.
Yeah, and they found these structures they called interstellar tunnels. You can sort of picture them as less dense pathways connecting the local bubble to other nearby cavities or bubbles.
Tunnels through space.
Kind of, like channels where the gas is thinner. And finding these actually supported an older idea from Cox and Smith back in 1974 that these large bubbles aren't always isolated. They might be formed by multiple supernovae, and the expanding shells can interact and merge, a bit like soap bubbles joining together.
Okay, so Hipparchus provided the map. But how do you then find the smoking gun, or I guess the exploding stars, the specific supernovae that created our local bubble?
Well, the focus naturally turned to those nearby OB associations, those clusters of young, massive stars, because those are the stars that go supernova.
Right, the Scosen association you mentioned earlier.
Exactly. Scorpius Centaurus. It's the closest OB association to us. Now, today it's about 130 parsecs away.
Still pretty far, but closer than others.
Yes. But there's a key study by Pellinis in 2001. They used that precious Hipparchos data, the positions and the motions of the stars, to essentially rewind time. They traced the movements of the sun and the stars in Scosen backwards.
Running the galaxy in reverse.
Basically, yes, using models of galactic motion. And what they found was fascinating. About 5 million years ago, the Scosen Association, especially a subgroup within it called Lower Centaurus Crux, was much, much closer to where the sun was back then.
Closer. How much closer?
Significantly closer. Close enough to make it a really strong candidate for being the source region of the supernovae needed to inflate the local bubble.
5 million years ago. Wow. Wow. Cosmically speaking, that's like yesterday afternoon. So these massive explosions happened right in our neighborhood, historically speaking.
Exactly. And other studies around that time, also using Hipparchos data, pointed in a similar direction. People like Benitez, Berghofer, and Breitschwert, Fuchs, they all suggested that maybe around 15 to 20 supernova explosions.
15 to 20.
Yeah, quite a few clustered in time, maybe happening roughly 10 to 20 million years ago.
Yeah.
And some of those explosions could have occurred as close as, say, 40 parsecs from the sun's past position.
40 parsecs. That's getting really close, less than 150 light years.
Yep, close enough to definitely carve out the bubble we see today.
This is incredible. Nearby supernovae, it really makes you stop and think. Could events that powerful, even that long ago, have had any consequences here on Earth?
That is a very good question and a really intriguing line of research. In 2004, Knie and colleagues found something pretty compelling. They analyzed a deep-sea ferromanganese crust. These things grow incredibly slowly on the ocean floor, layer by layer over millions of years.
Like a natural time capsule.
Exactly. And they found significantly higher concentrations of a specific isotope, iron-60. That's OFA.
Iron-60, why is that significant?
Because iron-60 is radioactive and is primarily produced in type 2 supernovae, the explosions of massive stars we've been talking about.
Yeah.
It has a half-life of several million years.
Okay.
So finding it on Earth in concentrations way above the tiny background level you'd expect from natural processes acts like a fingerprint. It's evidence of supernova debris raining down on our planet from a relatively nearby explosion.
A supernova fingerprint
Yeah.
embedded in the seabed. What did this iron-60 tell them?
Well, the peak concentration they found dated to around 2.8 million years ago. And the amount they found suggested the supernova happened within maybe a few tens of parsecs.
A few tens. So potentially even closer than 40 parsecs.
Possibly, yes.
Yeah.
Which fits perfectly with the idea that supernovae from Scosen were responsible for the local bubble and were happening relatively nearby.
Wow.
But what's even more mind-bending is that they pointed out this time period, around 2.8 million years ago, coincides with some interesting things happening on Earth.
Like what?
Well, potentially an increase in the cosmic ray flux reaching Earth, which a nearby supernova could cause. Also a noticeable climate shift in Africa towards drier conditions around that time. And possibly even a link to a marine extinction event that marks the boundary between the Pliocene and Pleistocene epochs.
Wait, so a star exploding dozens of light years away might have actually changed Earth's climate and affected life?
It's a distinct possibility. The evidence is suggestive, not definitive proof, but it lines up. The death of distant stars millions of years ago, potentially nudging the course of evolution on our own little planet.
That's humbling.
Puts our place in the galactic ecosystem into perspective, doesn't it?
It absolutely does. A profound connection across space and time.
Wow.
Okay, so for about 2 decades after these findings, the picture was sort of set then. Hot bubble, formed by supernovae, maybe affected Earth.
Broadly, yes. That general picture held a low-density hot plasma cavity surrounded by a shell of cooler gas and dust.
Huh.
But there were still uncertainties.
Such as?
The finer details, its exact 3D shape, precisely how far it extended in all directions, the exact timing of its formation, and importantly, how it really related to nearby star formation. Our knowledge of the local interstellar medium just wasn't precise enough to pin those things down perfectly.
Right, limitations in the data. And this is where the Gaia mission finally steps in, I presume. We hear constantly how Gaia is revolutionizing astronomy.
Precisely. Gaia has been transformative. It's given us radically new, incredibly precise information about the positions, distances, and crucially, the motions of billions of stars.
Billions with a B.
Billions with a B.
Huh.
The early data release 3, EDR3, provided just unprecedented accuracy for stars in our vicinity. And using this amazing dataset, Catherine Zucker and colleagues published a really groundbreaking analysis in 2022. They completely re-examined the 3D picture, the locations, the shapes, the movements of both dense gas clouds and young stars within about 200 parsecs of the sun.
200 parsecs. Okay, so zooming right into our local neighborhood with unprecedented detail.
Exactly, and their work allowed them to draw some really striking new conclusions about the local bubble.
Okay, I'm intrigued. How did they use this super detailed Gaia data to redraw the map of our cosmic backyard?
Well, first, they carefully selected a sample of over 1,200 stars belonging to known young clusters. These were stars with ages up to about 20 million years, located out to 300 or 400 parsecs.
Young stars, okay. Why young stars specifically?
Because they wanted to include stars associated with the known star-forming regions that seem to lie on the surface of the local bubble. Places like Lupus, Ophiuchus, Chameleon, Corona Australis, Taurus, and also older stars belonging to that SCOSEN association we talked about.
Got it. Linking the bubble's suspected surface to the stars there.
Exactly. Then, with this fantastic data set, super accurate positions and velocities thanks to Gaia, they did that traceback again. They ran the clock backwards for each cluster and for the sun, too, over the past 20 million years.
Using a model of the Milky Way's gravity again.
Yes, using a sophisticated model of the galaxy's gravitational potential to see how everything would have moved.
All right.
Basically, figuring out where everything came from.
Watching the cosmic movie in reverse, but with much higher definition this time.
A much better projector.
Yeah.
And they didn't stop there. They also ran computer simulations, hydrodynamic simulations, to model how the local bubble itself might have expanded over time if it was driven by a series of supernova explosions happening within a relatively uniform interstellar medium.
Trying to recreate the bubble formation virtually.
Right, and by looking at how much momentum would be needed from those supernovae to sweep up all the gas and dust we see in the bubble shell today, and matching it to the shell's observed expansion speed, which is around 6 or 7 kilometers per second.
Pretty fast, but maybe not as fast as you'd think for supernovae.
It's had millions of years to slow down as it swept up material. But based on that speed and the mass, they estimated that somewhere between 10 and 20 supernovae were probably needed.
10 to 20. Hey, that matches the earlier estimates based on the Scorpius stars.
It aligns remarkably well, yes. It fits with the number of massive stars we estimate were in those key subgroups, Upper Centaurus Lupus and Lower Centaurus Crux, that would have likely gone supernova over that time frame based on stellar evolution models and the initial mass function, how many stars of different masses typically form.
Okay, so multiple lines of evidence are all pointing to the same origin story now, and the numbers match up. What does the new picture of the local bubble look like based on this Gaia analysis?
The result is this incredibly detailed 3D model. We can now visualize the inner surface of the neutral gas and dust that forms the bubble's boundary. We can see the 3D shapes and pinpoint the locations of the nearby molecular clouds with a resolution down to about 1 parsec. It's stunning. They even made the model interactive and available online.
A 3D map we can explore. That's cool. But what was the biggest finding? You said there were striking conclusions.
Yes. Here's the really remarkable thing they found, something they called a major finding. Get this. Pretty much every single well-known molecular cloud within about 200 parsecs of the sun lies directly on the surface of the local bubble.
Wait, every cloud, not just near it, but on its surface. That can't be a coincidence, surely.
It seems highly unlikely. We're talking about all those famous star-forming regions in SCOSEN, Ophiuchus, Lupus, the Pipe Nebula, Chameleon, Musca, but also clouds like Corona Australis and even the Taurus molecular cloud, which is way over on the other side of the bubble from SCOSEN, about 300 parsecs away.
So they're all sort of draped over this invisible bubble.
That's exactly what it looks like in their 3D model. The only significant exception nearby is the Perseus molecular cloud, also about 300 parsecs out. But there's a reason for that, too. It looks like Perseus has been pushed aside by another, even larger structure called the Perseus-Taurus superbubble, which was only recently discovered itself.
A super bubble.
Wow.
Okay, so putting Perseus aside, all our local star factories, these molecular clouds where new stars are born, are literally sitting on the edge of this ancient supernova bubble.
That is the stunning picture that emerges from the Gaia data. And there's more.
Go on.
Zucker and the team also looked at the motions of the youngest stars within these clouds. And they found these stars show a pattern of outward expansion, moving mostly perpendicular away from the local bubble surface.
Expanding outwards from the bubble's edge.
Yes. And when they trace back the motions of these young stars, it strongly supports a scenario where the local bubble got started by a burst of star formation near its center, presumably in those SCO-SEN subgroups,
Right.
followed by the sequential supernova deaths of the most massive stars formed in that burst. This process seems to have kicked off around 14 million years ago.
Or 14 million years ago. Okay.
So the idea is supernovae go off near the center, create this expanding bubble, the shock wave sweeps up the surrounding gas and dust into a dense shell.
And then
That shell, under its own gravity and perhaps triggered by the ongoing pressure, fragments, and collapses, to form the very molecular clouds we see today, sitting right there on the bubble surface. And inside those clouds, new stars are now forming.
So the very explosions that created the bubble also triggered the next generation of star birth on its expanding edge. That is an incredible cosmic cycle of creation literally happening all around us.
Precisely. It provides really powerful, direct observational evidence for a theory astronomers have had for a long time, that supernovae can trigger star formation. We're seeing it happen in our own backyard. There's even a great animation based on earlier Gaia data, Gaia DR2, that gives you a sense of flying through this structure. You see the bubble, the clouds on its surface. It really brings it to life.
Amazing. So let us recap the big picture here. Our sun isn't just floating in emptiness. It resides within this vast, ancient bubble, hundreds of light years across, sculpted by the explosive deaths of massive stars, maybe 14 million years ago.
Correct. Shaped by the SCO-SEN Association's past activity.
And the most amazing part is that the surface of this very bubble is now acting like a stellar nursery, the place where most of the nearby new stars are currently being born.
That's the key takeaway from the latest research, largely thanks to Gaia.
It completely reframes how you think about our solar system's place in the galaxy. Not isolated, but intimately connected to these grand cycles of stellar life and death. Which really makes you think, given this history of pretty significant supernova activity relatively nearby, what might happen next? What future energetic events could reshape our cosmic neighborhood?
That's the question, isn't it? It's a pertinent reminder that the galaxy is incredibly dynamic, constantly changing, and that the story of our cosmic home is definitely not over. It's still unfolding around us.
A story written in the stars, and apparently on the seabed too, something incredible to ponder.